So work in general needs to be a change of energy of some kind, right? The change in kinetic plus the change in potential. So we had these separate equations. This is not one that I would maybe worry about putting on your equation sheet at this point, okay? This is not one that I don't think we'll use very often because we're going to move on to the conservation of energy equation, which is much more important. But essentially, you need to be thinking of work in terms of a change in energy, right? Okay, so your book talks a lot about conservative and non-conservative forces and how those affect work and things like that. I'm not going to go into that a whole lot, but basically you're looking at work done by non-conservative forces, which, for example, could be friction, tension, applied force, anything that is really coming into contact kind of with your object would be equal to this change in potential plus change in kinetic energy. Okay, this is something that your book kind of throws at us a little bit in terms of conservative and non-conservative forces. And I'm not too concerned with you knowing the difference between a conservative and a non-conservative force. But yeah, that's pretty much all I want to tell you with that. Okay, so work is a change in energy in general. That's kind of what I want you to start thinking of it in terms of. Okay? Sorry. Get whatever you need here. And then we're going to work on or look at the big picture for today, which is total energy. Okay. All right. So mechanical energy. Okay. This is what we're really focusing on now. If conservative forces are acting, those are things like gravity, right, which will be the most common thing we look at. The total mechanical energy of a system neither increases or decreases in any process. It is conserved. So this is our conservation of energy concept, right? And our law of conservation of energy. So when we are looking at things that move very simply from point A to point B, like roller coasters, right? Gravity is what is pulling a roller coaster kind of through its path. And this conservation of energy process or idea is why that is possible. Okay? So in the last slide when we talked about non-conservative forces, things like friction, all that kind of stuff, that's really not what we're focusing on here in terms of conservation of energy. We're looking mostly at gravity. Okay? But the mechanical or the total energy of a system should be conserved. If we talked about, last class we looked at that roller coaster problem and we talked about it gained potential energy or it lost potential energy. Right? Yet here we're saying the total energy of our system cannot be gained or lost. So what's happening to that energy? It's changing forms, right? So it lost potential energy as it went from its high point to its low point. It's lost potential energy. Would you agree with that? Can you remember that back a little bit? Okay, it lost potential energy. But what does that mean? It was gaining as it was rolling down that track. It was gaining kinetic energy, right? It was speeding up. So if we flip-flopped our thought process and we went from changing kinetic energy, right, it was at rest at the top, so no kinetic energy, to its top speed at the bottom. So that potential and kinetic energy kind of works on a sliding scale, right? We've got maybe at the top fourth of it, right, it's a fourth kinetic energy and 3/4 potential energy. And then as it goes halfway, you know, we reach the halfway point, all that kind of stuff. So we've got this transfer of energy. Okay, so the total energy of a system at one point is equal to the energy at one point of us in a system is equal to the kinetic plus the potential. Okay, this is at one point in our system. This would be if I stopped the roller coaster at this snapshot in time and I said it had this many joules of energy, right? That would be a combination of its kinetic and potential energy. Would you agree with that? Okay, so the one equation that we're going to work toward is the one on the bottom here. Okay, so you can put this one, that's fine. It's probably not equation sheet worthy just yet. But this is at one point in time. We rarely look at one point in time. Usually we're talking about a change that has happened, right? So since we say there's no loss in energy during a change, right? If something happens, there should be no loss in the energy of the system. That would tell us that the energy at the beginning should equal the energy at the end, right? Or the energy at any second point. So what I'm doing here is I'm just expanding that equation, right? If we know that E is equal to KE plus PE, all I'm doing is expanding that equation out. So this one, if you can't read it, is potential energy second, right? PE2. Okay, and you can put initial and final if that makes you more comfortable, right? I rarely use the 1 and the 2s, but your book does, so I kept them in there. We will always think of the left side of the equation being the initial side, and the right side of the equation will always be the final side. Okay, so I'm always going to put before on the left and after on the right. Okay, hopefully that makes the most sense to everybody as well. This equation, we're almost equation sheet worthy, right? We're getting close. I'm going to take it one step further now. At any point, we're going to look at kinetic and potential energy, and all I'm doing now is expanding out these equations for kinetic energy, right? Isn't the equation for kinetic energy 1/2 mv squared? And the equation for potential energy is mgy, right? So I'm expanding that out even further. So what do you think the next thing I'm going to do is? Right? If this is the energy at one point in our system, now I'm going to make it into final and initial. Okay? So here, this right here is the big one. This is what we need. We walked you through what it takes to get there. But now this is the equation that's going to go on your equation sheet, the one we will use over and over and over again. Okay? So this is initial energy equals final energy. Right? Kinetic plus potential equals kinetic plus potential. And this 4-term equation works all the time, right? Whenever we're looking at conservative forces, which are things like gravity, springs, we could use springs in here as well. So I can show you what you would need to substitute if we're going to use a spring, okay? So does everyone have this 4-term equation down? The only thing that would be different if we were looking at potential energy of a spring would be, we're not using gravitational potential energy anymore. We'd be using potential energy of a spring. So we'd say 1/2 kx squared. Right? Does that make sense? Instead of using potential energy of gravity, we would use potential energy of a spring. Okay, are we on the same page with that? What happens if I had a vertical spring? Because that might happen on your homework.
Do you spring with lines in it?
Kind of, almost. So if I have a vertical spring that hangs, isn't gravity acting on it and the object acting on it? So we would do plus 1/2 kx squared, right, on each side. So your 4-term equation would turn into 6. Okay? Rarely we see that, but I'm just warning you on your homework today that might happen. Okay? Just maybe. Okay? So let's try one here. I want you to remember again the sliding scale that happens with mechanical energy. As it hits the ground, right, or as it reaches the instant before it hits the ground, we're assuming all potential energy has been lost, right? We're talking about the instant before it hits the ground. It has all been transformed into kinetic energy at that point, right? Because its distance or its height off the ground is essentially 0, okay? So we're not talking when it hits the ground and comes to a crashing stop, right? We're talking about the instant before it has all been transformed into its kinetic energy. Okay? If a stone is held at 3 meters, calculate its speed when it has fallen to 1 meter above the ground. Okay, so we can't just use our kinematics equations here. We're going to use our conservation of energy equations, right? Theoretically, you could. But this is what we're learning about conservation of energy, so we're going to start there. Okay, so here's my stone. It's going to drop. Here's 1 meter. Here's 3 meters. Right, and here's the ground right here. Okay, you can choose, excuse me, we can choose to use the ground level as our real ground level. You can choose to use the 3 meter as your ground level. You can choose to use the 1 meter as your ground level. I really don't care, right? You read what the problem gives me and go with what I think is going to be the easiest. That's totally up to you. So I'll, for this one, probably just use the ground as our ground level. So let's think about, before we get started here, when it says it's dropped, what does that mean that it has, or it's held, whatever, it's at 3 meters. What type of energy does it have at this point? All potential. Okay? Then as it falls and it reaches this point, what does it have? Kinetic. Does it have any potential? Yes, it has both because it hasn't reached the ground yet, right? If it says it drops all the way to the ground, at that point we would have been transferred to all kinetic, but we're not there yet, okay? So out of our 4-term equation, kinetic plus potential equals kinetic plus potential, right? We don't even have to use this term because our initial kinetic energy is 0. Okay, so in your 4-term equation, it's likely that you won't have to use all 4. Okay, so just kind of pay attention to that. I like to put the 0 in just so I know, like, okay, I thought about it and I accounted for it, but it's 0. Okay, so our potential energy, we're just going to leave it as an M for right now because it didn't give us a mass. So times 9.8, right? mgy, our initial height was 3 meters. My kinetic energy is 1/2 m. We're solving for V plus m times 9.8 times 1. Okay, would you agree with where all those numbers came from? Okay. So I'm going to do the math, leave my m where it is for right now, and I'm going to show you how algebraically it will end up canceling. Okay, so on the left, that leaves me with 29.4 m equals 1/2 mv squared plus 9.8 m. Okay, from there, what should I do? I'm going to subtract over my 9.8 m. That would combine my like terms. Leaves me with 19.6 m equals 1/2 mv squared. So now I've got an m on both sides that I can cancel. Agreed? Okay. And then I'll divide over my 1/2. And then I square root that answer. And I get a velocity of 3.13 meters per second. That's not what you got? Oh, you're right. I divided by 2 instead of divided by 1/2. 19.6 divided by 0.5, that would make a difference. Thank you. 6.26? Okay, there we go. Sorry. 6.26. And what do I need to add to that?
Meters per second.
Okay, and going up or down?
Ooh, down.
Add the negative. Mm-hmm.
It's a close one.
So why is it still have?
Miss he said for.
All right. So again, this chapter has a lot of roller coaster type problems. Okay, at the top of the hill, what type of energy does it have?
Potential.
All potential, right? Because it says it starts from rest. At the bottom of the hill, what type of energy does it have?
Kinetic.
Kinetic. Okay, because that's the lowest point that it can reach, right? We're talking, even if that part of the roller coaster is still 5 meters off the ground, right? We're assuming that this is its ground level because we're hoping it doesn't go crashing off the roller coaster path, right? That track should keep it on track. It's not going to fall farther, we hope. Okay, that's the plan. So we'll assume that the bottom of that roller coaster is kind of its ground level. So here our 4-term equation goes from 4 to just 2, right? 0 kinetic energy plus potential, which is mg h, right, equals kinetic energy, 1/2 m, we're solving for v, plus 0 potential energy. So we can trim down that equation pretty often. So again, we're going to cancel our m's here. When we're moving on a roller coaster track, I'm less concerned with you saying that your velocity is negative because it's kind of going forward, right? It just so happens to be going down. When things become free falling, I would like for you to add the negative if it's going downward. Does that kind of make sense? So if it's following a path or a track of some kind, I'm okay with just keeping it positive because, you know, that's where it's supposed to be flowing, all that kind of stuff. If it gets to be a free fall type situation, I'd like for you to put the negative. Okay? So here, did we get 28 meters per second? Okay, very good. We're going to take this a little step further now. At what speed will at what height will the car have half of this speed? Okay, at what height will the car have half of this speed? How many of you think it's going to be halfway at the halfway point on our height? Yeah, maybe. Good. Okay, let's prove that. So, at what height will it have half the speed? Let me draw our little coaster again. Right, here's our roller coaster. We wanted to find somewhere along here where it's 14 meters per second, right? So we know if it's at some point along this path, it's going to have what type of energy? Both, right? It's going to have both, kinetic and potential. So when we set up our equation, we can go from our starting point, because we know it started at rest with all potential. So we can say 0 kinetic plus m times 9.8 times 40 equals kinetic. But this time we know the velocity is 14, and we're solving for the height. Okay, so we're just solving for the y value this time. All right, we're going to find how far above the ground level will it have reached this 14 meters per second, or half of that maximum speed. Okay, so that means it's only traveled 10 meters, but it's picked up not a majority, but half of its speed already. Okay, so as it continues to drop, it's going to pick up the remainder of that speed, but that's why you feel that kind of instant rush, right, when you start on a roller coaster. I'm not a roller coaster person, so I can't, relay that experience. But you feel a little bit more of a rush at the beginning because you're picking up half your speed within a fourth of the distance, right? So that's how it kind of works. Does that make sense? Okay.
Make a roller coaster feel.
No.
Promise I'll do problems while
This is a lot of words, and it seems like a difficult problem. It's really not that bad. Okay, so here's my spring. All right, and here's my dart. Here is the origin for the spring, right? So its displacement is this distance, right? And they told us is 6 centimeters. So we need to put that into meters. Okay, so 0.06 meters. Do we see, can we envision what's happening here? Okay, so this red line is where the spring would normally be. We've pushed it back, 6 centimeters to compress the spring a little bit. And then when we trigger, right, in a dart gun, we would pull the trigger, and that would release the spring. Okay, so after it travels and kind of hits this red line, then the dart releases, right, and it could go wherever it needs to go. Okay, so we are trying to find with what velocity would the dart leave kind of that gun at. Okay, so when it's coiled and when it's compressed, what type of energy does it have?
Potential.
All potential. Okay, and then as that spring reaches its equilibrium point and releases the dart, what type of energy does it have?
Kinetic.
Right, only kinetic. Okay, and all of that kinetic energy is transferred to the dart. Okay, because we're assuming there's no bounce back and forth on the spring, right? We're perfect physics world here. So as that thing reaches its equilibrium point, it transfers all of its energy to the dart, which would be all kinetic at that point. Are we on the same page there?
So dart wouldn't hold potential.
Nope, all of it, because at this point, when it reaches that equilibrium point, all of its energy is kinetic, and that's when the dart disconnects. So that all of that kinetic energy would transfer to the dart. Okay, so that means we would set up our potential energy, 0 kinetic plus potential. So is this gravitational potential or spring potential? So 1/2 kx squared equals 1/2 mv squared plus 0. The 250 is our spring constant, which is given to us here. Our initial displacement was 0.06, has to be in meters. The mass has a dart of 0.1 kilograms, and we're solving for velocity.
Will we usually be solving for velocity?
Not always. For some reason, that's what most of my examples were. But I wouldn't say that's a no.
So this one you have to know the mass, right?
Yeah, you have to know the mass. It won't cancel. Mm-hmm.
Oh, shoot.
So we had, did you remember to square root it at the end? So I ended up with about 3 meters per second here.